Yeah, I guess I will never finish the paper. There's always stuff popping out in front of my eyes. Extreme tech. This was some news which came around like yesterday. I noticed that in some feed or somewhere, I don't know, straight out of science fiction. I thought that's a science magazine. So let's talk about science fiction. Scientists create a crystal made solely of electrons. This site may earn affiliate commissions from the links on this page. Okay. Whatever that means. It's not often that messing around in the lab has produced a fundamental breakthrough, a la Michael Faraday with his magnets and prisms. Magnets? Breakthrough? Fundamental? What? Even more uncommon is the discovery of the same thing by two research teams at the same time. Newton and Leibniz come to mind. But every so often, even the rarest of events does happen. The summer of 2021 has been a banner season for condensed matter physics. Three separate teams of researchers have created a crystal made entirely of electrons, and one of them actually did it by accident. The researchers were working with single-atom thick semiconductors cooled to ultra-low temperatures. One team, led by Hong Kong Park, along with Eugene Demler, both of Harvard, discovered that when very specific numbers of electrons were present in the layers of these slivers of semiconductor, the electrons stopped in their tracks and stood mysteriously still. Eventually, colleagues recalled an old idea having to do with Wigner crystals, which were one of those things that exist on paper and in theory, but had never been verified in life. Wigner had calculated that, because of mutual electrostatic repulsion, electrons in a monolayer would assume the tree-grid pattern. Electrostatic repulsion. Park and Demler's group was not alone in its travails. A group of theoretical physicists led by Eugene Demler of Harvard University, who is moving to ETH Zurich, Switzerland this year, had calculated theoretically how that effect should show up in the observed excitation frequencies of the excitons. Excitons? Whatever. And that's exactly what we observed in the lab, said Atak Imamoglu, himself from ETH. Imamoglu group used the same technique to document the formation of a Wigner crystal. Electrons act like magnet poles in a way. Really? Electrons act like magnetic poles in a way. Electrons act like magnetic poles in a way. Wow. Like repels like. Like plus, minus. In solids, electrons help create regular, repeating crystal lattices. But it's a different story in liquids. Because liquid electrons are so easily disturbed when left to their own devices, their collective waveform is chaotic, full of shifting, uneven interference. Getting them to settle requires a perfect confluence of extreme conditions. First, it's easier when there aren't many other electrons to cause disturbance in the pattern. Also, neatly divisible number of electrons can be arranged in a perfect grid. An independent group of researchers, including correspondent author Fang Wang of UC Berkeley, were working with a semiconductor made of atom-thin layers of tungsten disulfide and tungsten diselenate. The atoms in those compounds are slightly different distance apart, so the overlapping layers create a honeycomb-shaped moire pattern of very slightly lower energy regions, which also help the electrons to settle down. Yeah, I guess you know how a honeycomb looks. A Wigner crystal of electrons red inside the semiconductor material. Then there is temperature. Everything slows down when it's very cold, so bringing the temperature within a few degrees of absolute zero helps to keep flighty electrons where they're supposed to be. This is where quantum phenomena start to supersede classical electron behavior. Instead of acting like wavefronts in water, the electrons start acting more in accord with their particle-like nature. But once it's cold and still enough, all of a sudden containing the electrons gets much easier. It becomes less like herding cats, more like those acoustic sandplate patterns. With the right number of electrons, they actually line up by themselves. Author's note. Electrons are the functional unit of electricity. Really? Yeah, I'm now really surprised. So it might seem like if you get a whole ton of electrons together, what you have is maybe something like ball lightning. Lightning? Electrons? Electricity? A potent, condensed, highly powerful quantity of electricity just waiting to sap something. But that's not what happens in a Wigner crystal. Electricity results from the movement of electrons, not just their presence. Correlating electrons together in a near atomic tree grid means that there is little movement of electrons within that material. It's also the definition of an insulator. That's how the researchers knew they'd created an electron crystal, where they've expected their semiconductor to semiconduct. It wouldn't. Hell, inside their pigeonholes, the electrons weren't moving, so neither was the electricity. These crystals are 100% electron, but they're insulators. Quantum fluctuations near absolute zero can cause quantum phase transitions between free-flowing liquids and quantum crystals, like Wigner crystals. These quantum transitions are believed to be important in many other quantum systems. Once they knew they had a Wigner crystal to explore its properties, the Harvard team decided to put it through quantum melting, which is apparently just like regular melting, but on a scale so tiny it's quantum. Are you kidding me? Like if you melt something small, it gets another name, and if it's really big, it's like, does it get another name? All this excitement took place on a scale so small that scientists couldn't visually imagine it even using the best light microscope, but initial attempts to use scanning tunneling microscopes destroyed the delicate surface of the crystal. This is right at the border of matter, of changing from partially quantum material to partially classic material, and has many unusual, interesting phenomena and properties. Said Temler in a statement. Exactly what those are will take some time to work out. Okay, let's hop over to another thing. Do you notice something? Nature is very, very well able to create Wigner crystals. Where we are. Noah. Yeah. It's just like, this is Noah and I am Ararat. I'm not the boat. Anyway. Yeah, they figured out that snowflakes are hexagons. So, I want you to listen to one dude which has really interesting things to say. So, Gerald Pollack, Weather and Easy Water, Electric Universe meeting, 2017.
Starts with this book that Don Scott mentioned, and we uncovered a different phase of water beyond solid, liquid, and vapor. And it's the basis, it comes from a lot of experiments that we did, and I think rather straightforward interpretations. And I just want to give you a summary without presenting the evidence for what we found. So we found that if there's water, and the water sits next to a hydrophilic material, in particular, not hydrophobic, but hydrophilic, water-loving, what happens is that the water transitions into a completely different structure, a layered structure, honeycomb kind of structure that builds in layers from here, one after another, and just keeps going on. And in fact, typically we find up to millions of molecular layers that undergo these transformations. We call them EZ, or exclusion zone layers of water, because we find experimentally that as the...
And I don't know, for some reason, it just really got this distortion. Like at this very moment, easy water means, what was it? Electrical, what? I forgot it. Exclusion zone. Yeah, that was it.
Grow, they push out all particles and solutes, so it's rather pure substance that we get here that's solute free. And the structure looks something like this. It's a hexagonal or honeycomb kind of structure, consisting, of course, of oxygen and hydrogen. And unlike the structure of liquid water, which sits out here. And it turns out it's not H2O anymore, it's actually H3O2. If you count the oxygens and hydrogens in a unit cell, this is what you get. And it's not surprising, because experimentally we found that this region has a net negative charge. And this is negatively charged. If to be neutral, it would have to be H4O2, that is double H2O, that's neutral. It's negatively charged. If you wanted this to be neutral, you'd have to put one more proton in here to make it H4O2. So, negatively charged, and the positive charges, complementary positive charges, lie here in the water. And the reason is that in order to build these, what happens is the water molecule is breaking into its component parts into OH minus, which sits here, lines up to give you this structure, and H plus, protons. So this is negative, and this is positive. And what that does is to form a kind of battery. This is the hydrophilic surface, this is the water, and this negatively charged EZ, or we call it fourth phase of water, is sitting...
Yeah, it actually stops here. You can watch the whole video. He was just about to explain that you can gain energy, electricity from water. So, let's hop over to the next thing. Wikipedia, once again. Honeycomb structure. Honeycomb structure are natural or man-made structures that have the geometry of a honeycomb. Oh, well. To allow the minimization of the amount of used material to reach minimal weight and minimal material cost. So, like, if you think about that, nature doesn't waste anything. Everything gets reused. Like, there's nothing wasted in nature, because nature is like a vast thing. It goes out to the universes and beyond. Everything is nature. So nature, since it doesn't waste anything, it probably, she, it, him, he, whatever, knows how to use stuff, like, really efficiently. So, the minimization of amount of material, like you can, there's nothing, no material or whatever, like, without matter. In every matter there is this certain kind of energy stored. It resonates with the environment, and like iron is really attracted to magnetics and these kind of things. So It shouldn't come to anyone's surprise that nature knows how to use its own resources in order to create things, like in the most minimalistic and simplistic way, hexagonal. The minimization of the amount of used material to reach minimal weight and minimal material. Yeah, it doesn't cost for nature, but that's important. The minimization of the amount of used material. And those other dudes, they made this wiggler crystal out of electrons. Yeah, obviously they relate to electricity. Easy water, what you just learned before, creates an electric tension, or like, you can gain energy from water. And now we were talking about small scale things like microscopic and all these kind of things. Saturn's hexagon. Saturn, it's big. And it has a hexagonal shaped pole. And there are really strong auroras here, and like there's electricity stuff going on. And those rings, what you see there in the background, there are like more like tubes, actually, I guess, or have been once, or will be again when we get hit by the galactic current sheet or whatever. There's a whole like stuff going on those planets electrically. Electrically. However you ever spelled it. Yeah, anyway, I leave it here. Hexagonals are the secret, or one of the best proof for the electricity of everything. And of course, if you take just one, you get a triangle. Then if you take 4 of it, you get a pyramid. Yeah. I'll leave it here. Thanks.